Okay, in this lecture, I'm going to continue this discussion we were having in the previous lecture about the dispersive effects of light on a non-conductive medium and how we can actually come up with a frequency or wavelength dependence to the permeativity. And we started with a model of electrons bound to molecules in a medium by kind of a spring force, and that the electromagnetic wave or the electric field that's oscillating through couples to that spring force and causes it also to be driven by some frequency omega. So here we came up with the amplitude of the displacement. It's a complex number, but where here is the form of it right here, and this is the amplitude. So what we can do next is say that the dipole moment is this vector complex. So the dipole moment with respect to time is the charge times the distance, which we can now rewrite as q squared over m divided by all of this frequency stuff times the electric field e to the minus I omega t. Okay, now if there are n molecules per volume, and there are F sub j electrons, so number of electrons, and omega j is the frequency for the jth electron. So basically this is number of electrons for the jth molecule. Then the polarization vector of the medium would be capital P nq squared over m, if I can factor that out, summing over the j electrons, fj, divided by omega j squared minus omega minus I gamma sub j times omega times the electric field. Okay, so now what we could do is we could rewrite this polarization in terms of the susceptibility, which is going to be a complex number, times the electric field. Okay, so if you remember that our permeativity is the permeativity of free space times 1 plus the susceptibility. And the dielectric constant, or relative permeativity, is the permeativity of the material divided by the permeativity of free space. So therefore, I can write the dielectric constant as 1 plus these terms in front, okay. So now we've worked that out. Sorry, not m. omega. So hold on, let me check my notes. Yeah, omega. Okay, so now for the dispersive medium, then what we have is the Laplacian of the electric field is basically this wave equation right here, where mu 0 is the magnetic property, but we're not going to worry too much about that, which means that I can now have a wave equation for my electric field of this form, which means that my K is the square root of epsilon tilde mu 0 times omega, like so. Now, this K tilde is different from the K tilde in previous lectures, where we talked about dispersion in a conductive material. Now we're talking about a non-conductive material. So it's a different K tilde, even though it's the same variable name used in the book. But we can still do the same thing that we did before. We can break this down into real and imaginary components, K and kappa. I can write out my electric field as the amplitude of the electric field, the dampening term, and my wave term, like so. Okay, and so this electromagnetic wave going into the non-conducting material is also going to be dampened out, like it was in the conducting material. And if I think about it, the intensity is proportional to the electric field squared, which means it's proportional to e to the minus 2 kappa z. And now I'm going to call the absorption coefficient alpha is equal to 2 kappa. So that absorption coefficient is going to be what's responsible for the dampening of the electromagnetic wave in the material. Okay, so now if I look at the index of refraction, n, that's just c divided by the speed, which in this term, this case is k divided by the frequency. So let's go back to the earlier definition of k tilde as the square root of epsilon tilde mu 0 times omega. And now I can rewrite this as the dielectric constant R times epsilon naught times mu 0. Let me clean that up. So it's epsilon naught mu 0 square root of that whole thing times omega. The square root of epsilon naught mu naught is 1 over the speed of light. So I get omega over c square root of the dielectric constant. Okay, so now if we put this into our equation, we get, basically have to substitute for the dielectric constant, which means I get a big square root, 1 plus n electron charge squared, divided by its mass, divided by epsilon naught, sum over all of these different electrons and molecules. To J, omega squared minus I gamma J omega. Okay, so now we have a relationship between this complex wave number and our frequencies. If we now want to expand this, so the square root of 1 plus a little number is equal, or approximately equal to 1 plus 1/2 times that little number. So if now I do an expansion, I get omega over C 1 plus n q squared over 2m epsilon naught, the summation like so. If I only take the real part of k, so I'm calling that just k, then what I get is an index of refraction, which is speed of light k over omega, which is 1 plus n q squared over 2m epsilon naught, the summation of f of j, omega j squared minus omega squared, squared, plus gamma j squared omega squared. Okay, let me start this again, because I'm running out of room. So basically I have to take the amplitude of it. I'm sorry, I have to get the real part, I have to take the norm. And so what I get is f of j omega j squared minus omega squared divided by omega j squared minus omega squared quantity squared plus gamma j squared omega squared. Okay, so I'm getting the real part of it. Basically, I have to use Pythagorean theorem on that. And now, if I look at the imaginary part, which is essentially kappa, then alpha is 2 kappa, which is equal to n q squared omega squared over m epsilon naught c. Take the sum over all of the electrons. Okay, so now I've got the imaginary part, I've got the real part. If I have the imaginary part, I therefore now have the absorption part of the wave. And so we now have a frequency-dependent index of refraction right there, basically the real part of my expression. Now, if we want to make an assumption, so let's assume that the dampening is small, so this part is much, much bigger than this part. So small damping. Then essentially my index of refraction is 1 plus n q squared over 2m epsilon naught, the sum of these terms right there. Okay, and so that's pretty much where we're going to stop. We now have a frequency dependence. You have to know a little bit about the material, but we can make some pretty good assumptions, and we can get an index of refraction, which essentially is 1 with these small corrections due to the frequency of the light.